Hi guys, so yeah, it's recording. So hi guys, today we are going to speak about measure. This is a concept that I honestly struggle a lot with. Even now, I struggle a lot with it. But recently, I found a kind of an example that showed how we can interpret what a measure actually is, and it suddenly hit me that when I realized what it actually is, that it's actually very simple, and somehow the textbooks don't make a good job of letting us know that it's simple. But when I go back now and read the textbooks, I'm thinking, okay, maybe I was dumb to not understand it, but I don't know. Anyway, so what I'm gonna show here is an example that I hope will help clear your doubts on what this is all about. Right, so let X be a non-empty set and S is equals to, oh my god, equals to, this is a sigma algebra, by the way. So if I graphically represent this, it is somewhat like this. So this here is X and this here is S. uh, as this might be something that could confuse some people. How come X is smaller than S? But it's literally over here that sigma algebra is something that contains the set itself, right? So this is not something very not something let's say complex. Anyhow, then let's continue with the question. Then mu is a measure that takes the elements in the sigma algebra and outputs something between 0 and let's say infinity. These are, by the way, bounded closed sets. Closed set, it's a closed interval, sorry, not a set. I'm so sorry, these terminologies confuse me sometimes because I'm, let's say, average. Such that mu of an empty set will give us 0 and mu of the whole X will give us 1. Okay, the measure on X will give us 1. So this is a measure on X. Now how do I go on about proving this proof? The proof is actually easy. I wanted to use the word trivial, but I kind of hate that word because sometimes I see videos and lecturers just use, yeah, proof is trivial and get ahead with it and without proving it. And you're looking at the board and thinking, okay, how is this trivial? So the proof is actually simple. By definition, we have that mu of the empty set is 0. So that's the condition 1. Before I actually prove it, I should do the good practice of uh, somebody just texted me on WhatsApp, I'm so sorry. Yeah, so the first condition, let's have a look at the definitions before I prove it. So yeah, uh, definition of a measure. So the first condition is that the empty set will have to output 0. This is already proven, by the way, in this question because we have this written here already. So the first condition anyway is proved, but I'm just showing, just this is not a form, I'm not writing it down here, but this is already proved. And 2 is that the second condition for something to be a measure is that the union, let's call the subscript I, from 1 to infinity, union of disjoint set, let's call it disjoint. So this is one way of writing it. When you write something, when you want to do something is disjoint, you can just add a plus sign in between the u, and this is ai will be equal to Oh no, I think my terminology might have been a little different. I just need to, yeah, I think the mu will be outs, not here. So I will just rub this whole thing off before. Yeah, I'm sorry for that. So this is how it is actually. I just messed it up. I'm sorry. So yeah, plus. Oh come on, this is a very okay. I'm now losing my mind. Anywho, 1 to infinity an. Oh, sorry, ai. This is equals to this is equals to the summation from 1 to infinity of sorry, this is the second condition. This is basically called countable additivity. What it means actually is that suppose we have a lot of let's call these sets A. So what this is trying to say us is that when you take the union of these sets, the red circles, you get this. It's basically like saying if I add these circles up, I will get this, which makes sense because you can see that they are disjoint here. But if they were joined, then it's some other case. Then we would need to do some more things, like let's say if I'm gonna digress a little bit here, but I hope it helps to understand. Let's say if this, okay, let's say if this is something, right? So let's call it a1 and a2. So here what we will do is when we define a1, we can actually define a new something. We can say it's b1 and we can say it's a1 without a2. I'm sorry, my sister had just interrupted me. Anyhow, so yeah, so now we will define something that is called b1, let's call it b1, and that will be basically a1 complement a2, means a1 without a2. And we can go on defining more b's, where we can define them in such a way that when you intersect those b's, when you intersect for example b1 and b2, it will be the empty set. But this is a topic for another day. Right now let's get back to what we were doing. Yeah, so we were trying to prove. Now I hope you understood what this is. This is basically saying that the unions of all the sets inside the sigma algebra should be equals to should be unions should be equal to the summation. So now let's go on and prove this. Okay, so proof 1, we can say by definition in the question, oh my handwriting, mu is equals to 0. That's done. Countable additivity. Now for countable additivity, I will once again draw this diagram so that I don't have to go up and down every time. So this is S again, this is, let's say, X. So how do you prove that this is countably additive? This is actually very simple. Look, on here we already have this condition. This is a very important, very critical condition. I think that just shaded this condition here. This says that when we take a measure on X, we will get 1. So it means that when this guy goes in this measure, it outputs 1, right? And similarly, from where we can see here that when this guy measures on the empty set, it gives you 0. Now from the question we know that we know that S contains only the null set, sorry, the empty set here, and X. So when I draw this diagram, you can automatically see that this outer area, this, what did I shade it earlier? I shaded it blue. This outer area here, this is nothing but empty set. This is nothing but empty sets. You can randomly pick any point from here. And so what I'm trying to say is that when this goes into mu, okay, I'll draw another one so that it's better. When anything from these blue shaded area goes to this measure, it outputs oh man, it outputs 0. So if you can understand what's going on in here, it means that now for me to prove that this is countably additive, I have to show that no matter what points I take in this sigma algebra, I will always end up with 1, because you can take 1 point from x, you still get 1, but you will take a million points from the blue shaded area, it will be 0. It doesn't make any difference. So in this scenario, we'll just do this. We will define a new variable. Let's see, let a1, we are gonna define more elements, empty set elements, so it doesn't matter how much you want to define. Let a from 1 to, let's say, a I minus 1 is equals to, let's say, they are the empty sets now. Okay, and then ai, let's say, is x. Let's say that what are the AIs here, by the way? I don't want to confuse you, so I'll just write, let's say this is one AI. Let's say these are all A's, and there are also A's here, one A here. But by the way, one very critical thing, there cannot be more than one A inside X, because one of the conditions is that it has to be disjoint. So in order for the whole thing to be disjoint, we cannot have another A inside X, because if you have another A inside X, it would mean that if you put a measure on this point, this is an X, right? So let me just change the color. So if you X, and if you take another, let's say, let me just do it again, let's do. So if you take X, let's say this one, and then this one, so this one, and then if you intersect with the intersection of this two, you get X, and that is not equals to the empty set. So that's the reason why, and this is where I was always confused. I was always asking this question to myself: why don't we take more than one element inside this X? But then later I realized that when you put them into intersection of X and X, it's gonna give you X, and that's why we cannot actually do that. But for example, if we are taking the intersection of this guy and this guy, it will give us the empty set, because the empty set and empty set intersection will be an empty set. So now AI, let's say 1 point. Now I'm gonna delete these things here. Let's say that, yeah, now let's say if AI is equals to X, now let's define the other values. AI plus 1 to a n is equals to the empty set. Now you can look at this and clearly see that no matter what I do, the union of these disjoint sets from 1 to infinity of these AIs will be equals to 1. Why? Because you can see here, there's just this one, only this guy has, actually I should use the terminology n here, because otherwise it makes no sense. Yeah, so, but yeah, in this scenario, I would say that this is 1, because of course these are all nulls, empty sets. So 0 0 0 plus, you can put infinitely many numbers of 0 and just have 1 and the answer will be 1. Similarly, when you look at the summation of this thing from n to 1 to infinity, you will see that, okay, now let's look at this an. Again, this will also be equals to 1. Therefore, we have proven that this is a countable additive. How this is one, again the same logic as the previous union example operation, that you cannot have a value different than one when you add up all of the sets inside the sigma, all of the sets inside the sigma set operations inside the sigma algebra, uh, because there's just one and zero zero, infinitely amount of zeros added to one is one. So I feel like I'm just repeating myself again and again. Anyhow, so this, we have proven that this is a measure. Once again, just for your clarity, no matter how many sets we take, we have already defined here that only one, there will be one such. This, I think I didn't do a good job at defining it, so rather than doing it this way, because I'm a bit I think that the terminology could have been a bit better. I could have just written then let a i's be equals to the empty set, and there will be at least one a that is in the x. This is all somewhat like the Dirac measure. And since we can't have more than one point inside x, because otherwise this condition will happen and then we won't have this one, and when we don't have this one, when the sets are not disjoint, we cannot have this countable additivity. So only in this scenario we can say that this is actually countably additive, and that concludes the proof. I hope I was able to explain this properly. Thank you.